Almost every major HPC cluster in the world has the same line written into its user documentation. Docker is not permitted on this cluster. This is not an arbitrary restriction. It is an architectural decision based on a fundamental conflict between how Docker was designed to operate and how shared HPC environments must operate for security reasons. But researchers and engineers still need containers. They need reproducibility. They need portability. They need to guarantee that the software environment running their simulation today is exactly the environment that runs on a different cluster 6 months from now. Singularity was developed at Lawrence Berkeley National Laboratory to give HPC workloads everything Docker offers, without the security model that makes Docker incompatible with shared clusters. Today I'm covering the full picture of containerization in HPC. To understand why containers matter in HPC, you need to understand the problem they are solving. In a traditional HPC environment, software is managed through a module system. Researchers load specific versions of libraries, compilers, and toolchains by running module load commands at the command line. The cluster administrator maintains these module files, and all researchers on the cluster share the same base operating system and the same set of available software versions. This model creates three persistent problems. The first is the dependency conflict problem. Two research teams that need different versions of the same library cannot have both versions cleanly available simultaneously without configuration complexity that grows with every added package. The second is the reproducibility problem. An experiment that ran correctly 6 months ago may not run today if module versions were updated. Reproducing results from a collaborating institution requires matching their exact software environment precisely, which the module system has no guaranteed mechanism to achieve. The third is the portability problem. A workflow built on one cluster frequently does not run on another cluster without manual reporting work because the available modules and their versions differ between facilities. Containers solve all three problems by packaging the entire software environment together with the application into a single portable unit. The base operating system files, all installed libraries, the runtime configuration, and the application binaries all travel together. The container image is the reproducibility guarantee. Whatever ran correctly in the container image yesterday will run identically next year on any compatible system. What is a container? Before comparing Docker and Singularity, I want to establish the shared technical foundation they both build on, because both tools use the same underlying Linux kernel features. A container is an isolated runtime environment that shares the host system's kernel but keeps its own file system, library stack, and process space separate from both the host and from other containers. This is fundamentally different from a virtual machine. A virtual machine emulates an entire hardware layer and runs a complete separate operating system inside it. A container sits above the host kernel and uses Linux primitives to create isolation without the overhead of a full OS virtualization layer. In practice, this means containers start in seconds and add minimal runtime overhead compared to running the same application natively on bare metal. A container image is the portable blueprint used to create containers. It is a layered file system snapshot containing the base OS files, all dependencies, the runtime configuration, and the application itself. That image can be shared, versioned, and deployed identically on any compatible Linux system. The Linux kernel features that make this work are namespaces and control groups. Namespaces create isolated views of the file system, the process list, the network stack, and user IDs for each container. Control groups, commonly abbreviated as C groups, enforce resource limits on CPU, memory, and I/O per container process. Both Docker and Singularity use these exact same kernel features. The critical difference between them is entirely in how each tool implements the user and security model on top of these shared kernel primitives. Docker and HPC. Where it struggles. Docker is the dominant container runtime in cloud and DevOps environments. Its tooling is mature. Docker Hub hosts millions of pre-built images for virtually every software environment, and most engineers already know how to use it. So what specifically prevents it from being used on shared HPC clusters? The answer is the Docker daemon and its root privilege model. Docker uses a background process called the Docker daemon that runs continuously as root on the host system. All container operations go through this daemon. When a user runs a Docker container, the daemon creates it with root privileges inside the container by default. Even when the user launching the container is an ordinary unprivileged user, the process inside the container can perform operations that are functionally equivalent to having root access on the host system. Certain privilege escalation paths have been demonstrated in practice across multiple Docker versions. In a shared HPC environment where hundreds of researchers access the same compute node simultaneously, this creates security risks that cluster administrators cannot accept under any circumstances. The second limitation is MPI integration. Docker's network model was designed for microservice communication over TCP and HTTP. It was not built to work with the high-performance cluster interconnects like InfiniBand that HPC applications depend on for low-latency cross-node communication. Forcing MPI workloads through Docker's virtual network layer removes the latency advantages that those interconnects were installed to provide. These two limitations, the root daemon model and the TCP-centric network stack, are not bugs in Docker. They are intentional design decisions for its original use case. They are simply the wrong design for HPC. Here is what surprises most engineers when they first encounter HPC containerization. The problem with Docker on HPC clusters is not performance. The container overhead of Docker in single-node workloads is generally under 2% compared to bare metal execution. The problem is entirely architectural. The security model that makes Docker simple and powerful in a developer environment makes it structurally incompatible with multi-tenant shared cluster policies. This means the solution to HPC containerization had to come not from patching Docker or working around its daemon, but from building a new container runtime from scratch with HPC constraints as the primary design requirement from the first line of code. That is exactly what Scilabs did when they created Singularity at Lawrence Berkeley National Laboratory. Singularity, built for an HPC. Singularity was developed specifically to resolve the conflict between container usability and HPC cluster security requirements. Its design makes three fundamental departures from Docker. The first is the rootless, daemonless model. Singularity does not use a persistent background daemon. When a user runs a Singularity container, the container process runs as that user with no privilege elevation of any kind. If you launch a container as a regular cluster user, everything inside that container runs as that same regular user. Cluster administrators can allow all users to run Singularity containers without any modification to existing cluster security policies, because Singularity never introduces root-level processes on shared nodes. The second departure is native MPI integration. Singularity was designed to work alongside the host system's MPI library, rather than replacing it with its own network layer. A Singularity container can directly use MPI processes running on the host, which means jobs spanning hundreds of nodes across InfiniBand interconnects run with full native interconnect performance. The third departure is the image format. Singularity uses a single immutable image file rather than a layered directory structure managed by a daemon. That single file can be stored anywhere in a regular user's home directory, versioned with standard file management tools, and shared directly between collaborators by simply copying the file. No registry infrastructure is required. If you are building the skills to design and operate real HPC infrastructure, subscribe and turn on notifications. Performance Engineering Academy is building a complete curriculum covering hardware performance, cluster architecture, distributed systems, and modern DevOps performance engineering. Every video in this series connects to the ones before and after it. So you are building a complete picture, not a collection of isolated facts. Now let me give you the direct side-by-side comparison and the exact workflow most professional HPC teams use to get the best of both tools. Docker versus Singularity. Direct comparison. Let me put the key differences on the table directly. On the security model, Docker defaults to root inside the container and requires a root-level daemon running on the host. Singularity runs the container process as the invoking user with no daemon and no privilege escalation at any level. On MPI and interconnect support, Docker requires complex workarounds to pass through native InfiniBand performance, and those workarounds often break cluster administrator policies. Singularity integrates directly with the host MPI stack and cluster interconnects with no additional configuration required. On GPU support, Docker uses the NVIDIA Container Toolkit, which requires daemon-level access to pass GPUs through to containers. Singularity supports GPU pass-through natively using a single command line flag that binds the host NVIDIA drivers directly into the container environment, and it works without any daemon on most HPC clusters. On image portability, Docker images are stored as layered directory structures managed by the daemon on each host. Singularity images are single files that can be stored anywhere on the file system and transported like any regular file. On ecosystem and tooling, Docker wins clearly. Docker Hub has millions of pre-built images for every possible software stack. Singularity can import Docker images directly from Docker Hub and convert them to Singularity format, which means the entire Docker image ecosystem is accessible to Singularity users without any manual porting work. This is the critical bridge that makes the two tools complementary rather than competitive. When to use each tool? Knowing the architectural differences, the right choice between Docker and Singularity depends entirely on which part of the HPC workflow you are in. Docker is the right tool for CI/CD pipelines that build, test, and validate your software before it reaches the cluster. Docker is the right tool for cloud burst workflows, where jobs overflow from the cluster to cloud compute instances on AWS, GCP, or Azure, because those cloud environments are Docker native. Docker is the right tool for packaging and distributing software to users who will run it on development machines and workstations rather than shared cluster nodes. Singularity is the right tool for everything that runs on the actual HPC cluster. Parallel MPI workloads that span multiple nodes across InfiniBand. GPU-accelerated training and inference on cluster GPU partitions. Long-running simulation workloads that must reproduce exactly across different facilities. Any workload that needs direct access to the cluster's high-performance parallel file system or its native low-latency interconnect. The practical workflow that most professional HPC teams settle on uses both tools in sequence. Build and validate in Docker during development and in the CI pipeline. Then, convert the finalized Docker image to Singularity format using Singularity's native Docker Hub import capability. Run the Singularity image on the cluster for all production workloads. This gives you the full Docker ecosystem and tooling for the development phase and Singularity's full cluster compatibility for execution. You write Docker images. You run Singularity containers. The workflow is clean, reproducible, and compatible with every major HPC facility's security policy. Let me walk through what this looks like in practice for a real HPC benchmark workload. Suppose you are running a distributed memory performance benchmark across a 16-node cluster, where each node has two NVIDIA A100 GPUs. You want to guarantee that the exact same software environment runs on this cluster today, on a cloud allocation next month, and on a collaborating institutions cluster at any point in the future. The workflow begins with a Docker image that captures your benchmark's complete environment. You specify the CUDA version, the MPI implementation version, the benchmark binary, and all configuration files. You build and validate this image in your CI pipeline with reproducible image tags for every version. This is where Docker's ecosystem advantage is at its peak. You get version-controlled images, automated test runs, and a complete audit trail. Before submitting to the HPC cluster, you convert the Docker image to Singularity format. The Singularity pull command accepts Docker Hub image references directly and converts them to the single-file Singularity image format. The resulting image file goes into your cluster home directory like any other file. Your slurm job script then calls the Singularity run command with the GPU pass-through flag enabled and binds the cluster's parallel file system to a path inside the container. MPI. Processes launch across all 16 nodes using the cluster's native MPI library over InfiniBand, achieving full bare metal interconnect performance inside the containerized environment. The container sees the fast file system. The GPUs perform at native speeds. The software environment is identical to what you validated in Docker. This is the full workflow. A question that comes up consistently in every HPC containerization discussion is how much performance overhead containers actually add compared to running workloads natively on bare metal. The answer from benchmarking studies conducted at major HPC facilities, including NERSC, is consistent across all workload types. For CPU-bound and memory-bound workloads, Singularity containers operate within 1 to 2% of native bare metal performance. The namespace and cgroup overhead at the kernel level is measurable in micro-benchmarks designed specifically to detect it, but it is effectively invisible at the application level for any workload running for minutes or hours. For GPU-accelerated workloads, the overhead depends on the driver pass-through mechanism. Singularity passing through native NVIDIA drivers directly from the host achieves GPU throughput within 1% of bare metal in standard benchmarks. The GPU hardware has no knowledge that it is operating inside a container because the driver path from the application to the hardware is direct. For MPI workloads, Singularity's host MPI pass-through model shows negligible overhead in benchmarking across clusters with InfiniBand interconnect. Docker's virtual network model in the same MPI workloads shows significantly higher latency because all inter-process communication goes through Docker's software network layer rather than directly through the InfiniBand fabric. The performance argument for Singularity over Docker in HPC is not that Singularity is faster in isolation. It is that Singularity can use the cluster's high-performance interconnect at its full rated performance while Docker fundamentally cannot. On a cluster where InfiniBand delivers 200 gigabytes per second, Docker routes that traffic through a virtual network, doing a fraction of that. That difference defines the entire practical performance gap. Let us bring it all together. Containers solve the three core problems of HPC software deployment: dependency conflicts, environment reproducibility, and cross-cluster portability. Both Docker and Singularity use the same Linux kernel namespaces and key groups underneath. The critical difference is in the security and user model built on top. Docker's daemon model and root privilege design create fundamental conflicts with shared HPC cluster security requirements. Singularity's rootless, daemonless design was built from the ground up for multi-tenant cluster environments. Singularity integrates natively with HPC interconnects and GPU hardware, delivering bare metal performance inside a fully containerized environment. The practical workflow that works in production is to build and validate in Docker during development, then convert to Singularity for cluster execution. You get the Docker ecosystem. You get Singularity's cluster compatibility. Both. The next video in this series covers checkpoint and restart mechanisms for long-running HPC jobs on preemptible cluster resources. If your workload runs for 20 hours and the cluster preempts it at hour 19, you need to know how to recover it without losing that progress. If this gave you value, like the video, share it with a colleague working on HPC workflows, and subscribe to the channel. Drop a comment telling me what container runtime your team currently uses on your cluster. I read all of them. Keep engineering. Keep performing. See you in the next one.